Today we are talking about applications of the electric potential and electric potential energy. And that brings us to talking about the capacitor, which is a device that is used to store either charge or electric potential energy. And in its simplest form, a capacitor is two conducting surfaces separated by some distance. And so a common capacitor is known as the parallel plate capacitor, where you've just got two parallel conducting plates, some separation d apart, and these two conducting surfaces have some charge. One of them is positively charged, the other is negatively charged. And in this case, the plate is connected to a battery, which is essentially producing that charge differential. And then over here on the right, there's a slightly more complicated capacitor setup where there's multiple layers of conducting material with an insulator in between. And so the idea here is that these things can be a little more complicated, but essentially we want to just think about the simplest cases where we've just got two conducting surfaces. So the capacitance is a quantity that allows us to describe the ratio of the maximum amount of charge that can be stored on a surface compared to the voltage difference between the surfaces. So this is known as the capacitance, the ratio of Q to, the book uses V here, but really what they're referring to is delta V, the voltage difference between the two plates. And capacitance is in units of coulombs per volt, which is known as a farad, named after Michael Faraday, who was one of the pioneers in studying electromagnetism. So a few things to note. The farad is very large. Typically our capacitance values are going to be in the micro and sometimes all the way down to the picofarad values. And also, capacitance is a purely geometrical property. And what do I mean by that? I mean the capacitance is entirely determined by the size, the shape, and the separation of the surfaces. So the geometry of the conducting surfaces is essentially what sets the capacitance. Now, we're going to talk about three common types of capacitors. I already showed this one. The parallel plate capacitor is probably the most common type of capacitor that we'll see in examples and in applications. And so we're going to write out an expression for the capacitance for this particular setup. And so remember the definition for capacitance. And then also remember that the electric field between two charged plates is sigma over epsilon naught. That E field is uniform, and remember sigma is the charge density, that's Q over A. And so since the E field is uniform between these charged plates, that means the potential between the plates is E times the separation. And so we can substitute in sigma over epsilon naught, and we can get this expression for the potential, the electric potential between the plates, right, at any this is, I guess, the potential difference between the two plates. And so go back to the definition of the capacitance, plug in for the potential difference, and then end up with this expression. And so that's where this final expression for the capacitance for a parallel plate capacitor comes from. So the capacitance is purely determined by the geometry of the plates, their surface area A divided by their separation D. Two other examples. The spherical capacitor. Now, the spherical capacitor is two spherical shells, radius R1. So in this case, R1, the sphere at R1 has been positively charged, and then a sphere at R2, which in this case has been negatively charged. And so The integral is done in the book. I didn't reproduce it here, but the integral done to determine the potential difference between the potential at R1 and at R2 is done in the book. And when you essentially plug in for the capacitance, you end up with this expression for the capacitance of a spherical capacitor. Again, you can see the R1 and R2 in the top, so that's essentially taking into account the surface area of the capacitor, and then also this R1 minus R2, which is taking into account the separation. And again, slightly different expression than the parallel plate because the geometry is slightly different. The third common capacitor that we might see is a cylindrical capacitor. And so a cylindrical capacitor, we've got an inner cylinder, in this case positively charged, and then an outer cylinder, the opposite charge. And so the inner cylinder we're calling radius R1, and then the outer cylinder radius R2. And again, the integral to determine the potential difference between the potential at R1 compared to R2 is done in the book. I didn't reproduce it, but again, the end result is that the capacitance, for a cylindrical capacitor is given by this expression here. Again, the capacitance depends on, now in this case, the related to the length of the cylinder, and then also taking into account the ratio of R1 to R2, and then the natural log is coming about from taking the integral of the electric field due to a cylinder, which drops off as 1 over R. So when you take the integral of that, you end up with the natural log. All right, last up is a discussion of the work required to charge up a capacitor, which is then directly related to the potential energy that's stored in a capacitor. So the first thing I've drawn here is 2 parallel plates with net charge 0 on each. And I want to talk about, all right, if I take a little chunk of charge from the right surface and I move it over here to the left, how much work does that require? And if you remember, energy and the electric potential are connected by a factor of Q. And so the little amount of work that I'm doing, right, is related to the potential difference between the 2 plates, and then multiplied by the little dq, the charge that I'm going to be moving. And of course, sometime later, I've charged up the left plate by some amount plus q, which means the right plate is now negative q, because I've been taking the charge from the right plate to put it over on the left. And so now the question is, all right, well, how much work is it going to require to take another chunk over? Well, now, when I go to take this over, there is more charge over on the left-hand plate than there was earlier, so it's going to require more work for me to bring this over. Still the same expression, it's just that the amount of work is going to need to be more because there's more charge over on the left-hand side. Effectively, you can think of repelling that dq charge, so it's going to take more work. Now, how do we do the calculation? Well, basically, I want to integrate this small amount of work I'm doing all the way from adding 0 charge all the way to the total amount of charge, big Q. And so I'm going to substitute the work expression for V dq. Then I'm going to substitute the capacitance expression for V. I'm going to substitute that in, Q over C. And then I'm going to do the integral Q dq. That gives me 1/2 Q squared. And I still have that factor of over C. And so that's what I get for the work required to charge up a capacitor with capacitance C up to a charge Q, 1/2 Q squared over C. But the work needed to charge up the capacitor is the same as the charge that's stored in the capacitor. And so that means the potential energy stored in the capacitor is 1/2 Q squared over C, or if you plug in the definition for capacitance, you also have these two other expressions that are equivalent to talking about the potential energy stored in the capacitor, 1/2 CV squared or 1/2 QV. So each of those three represents the potential energy stored in a capacitor.